Does anyone have any questions from the lab or from the last lecture? Homework? If you haven't picked up your graded homework 3, you can do so after class. It's right there. If you haven't picked up 1 or 2, it's also in there, stacked together.
How many points is this homework at?
So I'll post the rubric. Yeah. I'll post. I've just been posting the rubric for all of them. I think it's 90. Oh yeah, so you can know your averages. I guess that would be good. Yeah, 90. It's on Canvas as well. Yeah, how many points it's out of. Yeah. Okay. All right. No questions? So last lecture, we normalized the boundary layer equations, and we kind of uncovered some dimensionless parameters, namely the Reynolds number and the Prandtl number. And we talked about how we can calculate those two dimensionless parameters for different geometries given fluid properties and knowledge about the flow speed, etc. And using those two parameters, we can calculate things like the friction coefficient. So right here we wrote down how the friction coefficient was a function of these dimensionless parameters. And then the Nusselt number as well. So it's some function of these dimensionless parameters. And that for given geometries, we will figure out what this function is equal to. So then we'll be able to calculate these two numbers, the Reynolds number and the Prandtl number, from knowledge about the flow situation, knowledge about the problem, calculate the Nusselt number and the friction coefficient. From that, calculate H, the convection coefficient, and then we can calculate Q, the heat flux or heat rate. And then from the friction coefficient, we can calculate the skin drag. So that's kind of where we're headed with all this. So first, today we're going to talk initially about, give a little bit of a physical interpretation of the dimensionless parameters. So just typically dimensionless parameters are a ratio of like one force to another or a stress to another. So we'll talk about what those mean kind of physically, what they're ratios of. And then we'll start into kind of the simplest force convection, where we talk about flow over a flat plate, and write down some of the functions that will enable us to calculate the Nusselt number and the friction coefficient. Okay, so we'll start with physical interpretation of the dimensionless parameters. And are you all familiar with what I'm talking about when I say dimensionless? It's like there's no units, right? So we non-dimensionalize the boundary layer equations by, for example, taking the x position, which has units of meters, and dividing it by some characteristic length, which has units of meters. So you're left with these equations that don't have any units, because they're just ratios of one thing to another that have the same units, so it cancels out. So that's what dimensionless is. Okay. So first, the Reynolds number, which we've mentioned before, but it's pretty significant. So we'll just go ahead and write down explicitly what the Reynolds number is expressing in terms of ratios. So writing it down like this, it's some Reynolds number over a length L. And it's the ratio of inertial to viscous forces. So the top here is some measure of the inertial forces within the fluid. And the bottom, this is just viscosity. So the inertial forces you can think of as being related to momentum. And the viscous forces, obviously, related to viscosity. So then for large Reynolds numbers, you would expect the inertial forces to be dominant. And then for small Reynolds numbers, the viscous forces dominate. And we talked about how the Reynolds number of a flow influences its transition to turbulence and whether or not it transitions to turbulence, and if so, where that transition occurs. So we said there can be some flow disturbances, and if the Reynolds number is really low, the viscous forces would tend to attenuate those and prevent or delay a transition to turbulence. If you have a high Reynolds number, the inertial forces and the higher momentum of the flow kind of exaggerate those disturbances and cause a transition to turbulence to occur either more quickly or a higher likelihood of it occurring. Yeah.
Can you just remind me what we define as large and small for Reynolds numbers, or is it dependent on the material?
So we said the critical Reynolds number, so the Reynolds number at which the transition to turbulence will occur, is 5 times 10 to the 5th. I think that's right. Let me check real quick. Don't want to write down the wrong thing.
So that's like the boundary between large and small.
Yeah, at least for flow over a flat plate, that's kind of what you can think of as a large Reynolds number versus a small Reynolds number. Yes, 5 times 10 to the 5th. So that's the critical Reynolds number where transition occurs. Yeah. So we'll say influences transition to turbulence. And then it also influences the boundary layer thickness. So if you have a higher Reynolds number flow, tends to cause a thinner velocity boundary layer. Okay, the second dimensionless parameter that we're going to talk a lot about is the Prandtl number. And that is, PR is the kinematic viscosity, nu, over alpha, where we talked about on Wednesday, this alpha is the thermal diffusivity, which we talked about, I think, during the first or second week. So thermal diffusivity, and it's defined as K over rho Cp. So how quickly a material conducts heat versus how well it stores it. And the Prandtl number is kind of gives you a measure of the relative effectiveness of momentum and energy transport. So it's kind of the ratio of the effectiveness of momentum transport to energy transport. So ratio of effectiveness of momentum to energy transport. In the velocity boundary layer and the thermal boundary layer, respectively. So the effectiveness of momentum transport in the velocity boundary layer to energy transport in the thermal boundary layer. So it's going to influence the relative growth of these two boundary layers. So how quickly one boundary layer grows relative to the other. And kind of an interesting I guess examples of that are liquid metals versus oils. So for liquid metals, they have a really small Prandtl number. Because the basically energy diffusion in a liquid metal is much faster than momentum diffusion. So you end up with a much higher number in the denominator. I'm just going to write, rather than much less than or greater than 1, I'll just say small Prandtl number and large Prandtl number. So I'm not exactly sure how that lines up. It should be much less than or greater than 1 because it's the ratio. But oils basically have a much higher momentum diffusion than energy diffusion. And gases are usually a Prandtl number of around 1. I think for air it's like 0.7, because they're kind of equally good at transporting momentum and energy. Make sense? Okay. All right, so we're going to start talking about our first kind of geometry for forced convection and write down some functions that allow you to calculate the Nusselt number and the friction coefficient. So you can actually start solving convection problems. So we're going to start with forced convection and external flow. These are basically the kind of the simplest convection setup that you could have. So what makes external flow kind of simpler than another type of flow, for example, internal flow in a pipe, is that the boundary layer isn't constrained by any adjacent surfaces. So you just have the boundary layer develop naturally, and the flow, velocity, and temperature just kind of recover to the free stream values and you don't have to consider, how close you are to another solid surface. It's just one solid surface with the boundary layer developing naturally. So we'll say the boundary layers are not constrained. And then outside of the boundary layers, velocity and thermal gradients are negligible. You just have free stream conditions. And we're going to specifically consider low speed, forced convection with no phase changes. So nothing is evaporating or condensing or reacting or anything like that. And like I said, what we want to do is determine the functions that relate the Nusselt number and the friction coefficient to the Reynolds number and the Prandtl number. And there are two methods of doing this, two primary methods. The first one, which we'll mostly focus on, is experimental or empirical. So remember, we're trying to specify a geometry and then figure out these functions that allow us to calculate the Nusselt number and the friction coefficient for that geometry for any fluid, any flow speed, any kind of geometric scale of that geometry. So experimentally, how you do that is basically perform lab experiments using a bunch of different sizes and flow speeds and fluids, and kind of cast the results in terms of the relevant dimensionless parameters, the Reynolds number and the Prandtl number, and you'll hopefully get some sort of trend that kind of where everything collapses onto one curve. You can kind of write an equation to say, okay, so the Nusselt number or the friction coefficient is equal to this kind of empirically determined coefficient or power of the Reynolds number and the Nusselt number. So let's say this basically results in expressions for the Nusselt number and the friction coefficient. And then from those, you can calculate the convection coefficient and the skin drag. The other way we can do this is theoretically. So for really simple geometries, and kind of very simplified flow situations, laminar flow, etc., we wrote down the dimensionless boundary layer equations, right? Those are just differential equations, and you can apply boundary conditions, and you can solve them, and you can directly solve for the temperature and the velocity distributions, which is kind of what we've been doing previously in kind of simpler setups with conduction and whatnot. So for specific applications, you can solve it this way. Directly solve the boundary layer equations and get U, V, and T. And then once you know that, like we've done before, you could just differentiate. If you know the temperature distribution, you can just take the derivative with respect to X or Y, and then plug that in and directly calculate the friction coefficient, or the convection coefficient. So these methods you solve the boundary layer equations for velocity and temperature fields. So U of X or Y, or however many dimensions you're considering, and T of X, Y. Then, if you want to cast it in kind of more general terms, so you can take those results and apply them to different scales, then you can calculate H and the kind of dimensionless parameters. So it's a little backwards from the previous method. But both ways get you kind of the same solution that you're looking for, the Nusselt number and friction coefficient as functions of these dimensionless parameters, and then you can apply that result to other scales. And as we said before, we'll talk about solutions for a lot of different geometries, so it's important to know the assumptions and geometries match up with the equation that you're using. And we're going to have to look up fluid properties pretty frequently. You need to know the viscosity, the density, the Prandtl number. So as I mentioned, I think on Wednesday, the fluid properties do vary with temperature, and we're going to evaluate them at this film temperature. Which is defined as the surface temperature, the solid surface temperature, plus the ambient temperature divided by 2. So just the average of the surface and ambient temperatures. So what we're talking about, remember, is the fluid in the boundary layer. And that fluid is going to have some temperature in between the surface and the fluid temperatures that is kind of unspecified. That's what we're calculating. We're trying to find the temperature distribution. Since we don't know it, we're just going to say, okay, the best, easiest method to do this with pretty good accuracy is just to use the average temperature of the surface and the fluid and assume that's good enough. There are some situations, there is one problem in your homework, for example, where you don't know the surface temperature and that's what you're solving for. And those are a little more annoying because you have to either guess or just use the ambient temperature, for example, find the fluid properties, calculate the surface temperature, and then basically iterate. So you calculate the surface temperature based on just like a guess of what the fluid temperature, or a guess of what the film temperature will be, or just using the ambient temperature. Look up properties at that incorrect temperature, solve for the surface temperature, then you can calculate the film temperature and iterate until it kind of converges.
How do you know what your goal is? Sorry.
When you, basically when your answer stops changing
Oh,
within like a degree or whatever you think is reasonable. Yeah.
Use MATLAB or Excel for that?
Sure. Yeah. I mean, honestly, the thing that takes the most time is looking up the
Yeah.
properties at the different temperatures. And once you have done that, it's really just like one equation. So, but yeah, I mean, do it however you want. Yeah. Okay. So we'll talk about now our first geometry and actually write down some functions. So we're going to consider laminar parallel flow over a flat isothermal plate. So we're talking only about laminar flow for now. So this is going to only apply to the region less than the critical x location. So transition to turbulence occurs at this x sub c, which is determined by that critical Reynolds number, 5 times 10 to the 5th. So the equations that we're going to write down here are only for x is less than x sub c. So if you're going to work a problem, you would want to first check where the transition to turbulence occurs, and then figure out which regime you're in. And then if you're in laminar, use the laminar equations. If you're in turbulent, use the turbulent equations. So for this geometry is one of the few that the book actually goes through and solves theoretically. It's a simple enough setup, laminar flow, that you can actually solve it exactly using a similarity solution. I specifically remember going through this in graduate fluids, so I think I'm not going to write it all down here. I don't think it would be a good use of time. If you want to read it, it's section 7.2.1 in the book. I see you're all writing that down. Yeah. Okay, so you can solve it theoretically and basically get these same results out, the Nusselt number and the friction coefficient. So we're just going to write down what those results are. Yeah.
how long did it take you to do that?
Did it take me to do it?
Yeah, in graduate school we solved it.
Oh, I mean, my homework usually took me like, I don't know, 48 hours or something, like solid. Like, I don't know. Yeah, it would be like 24 pages of engineering paper. Yeah. I think like for a similarity solution though, we like went through it in class and he like derived. Yeah. Aliseda. It's a good class. Yeah, learned a lot. Yeah. So, we're just going to write down the results. So, we're going to assume basically this solution was constructed for steady, incompressible, laminar flow with constant fluid properties negligible viscous dissipation And we're going to assume that the pressure gradient in the x direction is 0. So just that there's no kind of changes in the pressure in the x direction or no changes in the potential energy or anything like that. So our velocity boundary layer results. So we get expressions for the boundary layer thickness. Which is 5 divided by the square root of u infinity over nu times x. Which, if we want to cast this in terms of the Reynolds number, 5x over the square root of the Reynolds number. So you can see the boundary layer thickness now decreases with increasing Reynolds number, which is what we wrote down previously. So we're also often interested in the shear stress, and we're going to write down expressions for the local and average values of most of these parameters. So we'll specify that this is local. And for boundary layer thickness, it's kind of always local because you're just interested in what the thickness is at that one location. So local surface shear stress. So that's 0.332 u infinity times the square root of rho mu u infinity over x. And this is a 0 out in front. So from the shear stress, we can get the friction coefficient. So the local friction coefficient. And that is C sub f, we'll say C sub f comma x, so just specifying that it's at a particular x location, is 0.664 times the Reynolds number, so this is Reynolds sub x, so again, Reynolds number at a specific x, to the negative 1/2. 0.664 Reynolds number to the negative 1/2. Yeah.
Surface shear stress, is that rho mu u infinity all over x?
Yes. So then the average friction coefficient denoted by the bar, is 1.328 times the Reynolds number to the negative 1/2. So it actually ends up just being double, basically, what the local convection coefficient is. And this is obtained just from integrating. All right, so we have thermal boundary layer results. So again, boundary layer thickness. So the thermal boundary layer can be solved just by relating it directly to the velocity boundary layer. This is more of an approximation. But the expression that we wrote down for the velocity boundary layer, if you calculate that, then you can calculate the thermal boundary layer just from the Prandtl number. And this is applicable for Prandtl numbers greater than approximately 0.6. And there are frequently going to be restrictions on the range of the Prandtl number or Reynolds number that a specific expression is appropriate for. So you need to make sure that you're in the correct range before using it. So the local Nusselt number is equal to 0.332 times the Reynolds number to the 1/2 times the Prandtl number to the 1/3. And again, applicable for Prandtl numbers greater than approximately 0.6. And then we can also get the average Nusselt number. And so, just to make sure we're clear on the difference, the local would be the Nusselt number at a particular x location that you specify. And then the average Nusselt number is the average over basically 0 to whatever that x location is. So the Nusselt number at one specific location, so the convection coefficient at one specific location, versus the average over the entire distance of the plate from, for example, the leading edge to the point that you specify. So when you're specifying an x here to calculate the Reynolds number for the average Nusselt number, so let's write this down first. Average Nusselt number, 0.664, Reynolds number to the 1/2, Prandtl number to the 1/3. And so you're going to have to specify an x to calculate the Reynolds number, because it has kind of the x dimension and the length dimension in it. And for the local Nusselt number, if you're specifying an x, you're saying, okay, this is a Nusselt number at that x location. But if you use the same x value and plug it into the average Nusselt number equation, you're going to get the average Nusselt number from 0 up to that x location. It's kind of a key difference. Yeah.
That also has the same Prandtl requirement? Or?
It does, yes. I just did not write it down. Thank you. And also for Prandtl number greater than 0.6. So this is kind of the point of heat transfer or the point at heat transfer where you get a bunch of empirical relations. We just kind of write them down, and you know that they come from either a direct solution to the boundary layer equations or from some lab experiments. And really the tricky part is knowing how and when to apply them and using the correct ones for the correct problem.
Is it just coincidence that the coefficient for these are the same as the shear stress and friction coefficient, or is there like a corollary between the two?
That's a good question. I actually hadn't noticed that. I would guess that it's not a coincidence. Yeah, I'm sure it comes from the math. Yeah. Yeah, so the average is double of the local, which comes from integrating. But yeah, I hadn't noticed that the coefficient is the same between the shear stress and the boundary layer, which is interesting because it's in the two different boundary layers. Yeah. Okay, so let's see. We wrote down the average Nusselt number. And so this Prandtl number restriction basically restricts you to Prandtl numbers greater than 0.6. So if you have fluids of low Prandtl number, like liquid metals, for example, you need a different correlation. So fluids of low Prandtl number. For example, liquid metals. So for liquid metals, basically diffusion of energy is much faster than diffusion of momentum. So the thermal boundary layer development is going to be much more rapid than the velocity boundary layer development. So at any particular x, because diffusion of energy is much faster than diffusion of momentum, the thermal boundary layer is going to be much thicker than the velocity boundary layer. So if you think about what that means physically, you have a really thick thermal boundary layer, a really thin velocity boundary layer, and you can essentially say that the velocity in the entire thermal boundary layer is just equal to the free stream. Yeah, because the velocity boundary layer is so thin that it occupies a very small portion of the thermal boundary layer. So basically the velocity in the thermal boundary layer is equal to the free stream. So U in thermal boundary layer is equal to U infinity. And that allows you to come up with some a kind of different solution for the Nusselt number. So for this, the local Nusselt number is 0.564 times the Peclet number, new number, for very small Prandtl numbers, so less than 0.05, and for Peclet numbers of greater than approximately 100. And this PE is the Peclet number, which is just the Reynolds number times the Prandtl number. Someone decided that it needed to be its own number, and it needed to be named after them. I don't know, I assume that's what happened. It probably has other significance. Okay, that's it for laminar flow. Let's write down a few correlations for turbulent flow. So now we're going to be in the region past the critical X, so past the transition. So turbulent flow over a flat isothermal plate. So now we're talking about, this applies to from X sub C to L. So whatever the length of the plate is, the end of the plate. This critical point up to L. So the laminar results were obtained analytically from this similarity solution, but you can't obtain exact analytical results for turbulent flow because it's inherently unsteady. So these results come from experiments, so they're empirical. So we have, again, local friction coefficient. C sub F is equal to 0.0592 times the Reynolds number to the negative 1/5. And this is for Reynolds numbers that are between the critical Reynolds number and 10 to the 8th. We have the velocity boundary layer thickness. (0.37x) times the Reynolds number to the negative 1/5. And if you look at the expression for the velocity boundary layer thickness in laminar and turbulent flow, it's much more rapid in turbulent flow. The growth is kind of determined by random fluctuations of the fluid rather than by just diffusion of momentum. So that's why you don't have the Prandtl number showing up here, because diffusion isn't really important in the turbulent boundary layer growth, and the Prandtl number is just the ratio of the momentum and energy diffusion rates, basically. And since that doesn't determine boundary layer growth in turbulent flow, it's just an expression of the Reynolds number. So we'll note that it's not a function of the Prandtl number. Okay, any questions? Okay, so we'll start back up on Monday talking about turbulent flow and mixed boundary layer conditions when you have laminar and turbulent. Tuesday we'll do some practice problems and midterm review, because the midterm is the next week, November 5th. And please pick up your homework. Thanks.